some possibility that if I can't make it in time, then there will be a, let's say, normal exam, so that you should come to the university and write the things in paper. But the aim is that it would be online exam.
Will we be allowed to use materials from the lectures?
If we have an, let's say, normal lecture or a normal exam, so that you're sitting in a classroom, then I will provide you this formula sheet. Maybe I will share the screen so that you will see. So at the moment, this is the contents of the course. I haven't changed anything yet. It's updated on 7th of January. And these are the things that we have gone through. And here it says that on next week we should have an exam, but we haven't talked about hydraulic fluids at all, and we have still some calculations that we haven't gone through, and we need this week and next week to do these things, and that's the reason why we have to move this exam to here, week 10. Okay, but then about the material, here in Moodle first page is a sheet called, or a Word document called formulas. And this is the document that you can have during a traditional exam. The only document what is available for you. So if you are doing it at home, at university, you will get these formulas for you. But then if the case is that you're doing it at home, I'm not able to control whether you use the material or not, and that's the reason that I need to design the exam in a different way so that you are allowed to use all material. Then the questions just will be a little bit different, maybe a little bit more complex.
Okay, thank you.
Excuse me, one more question.
Yeah.
Like if we're doing it in school, do we able to use FluidSim in the computer, or we cannot use that?
You can't use FluidSim. If you do the exam at school, then it's fully a written exam, so that you have just a piece of paper and a pen, and you need to write down. There are some calculations and there are some theory questions where you need to give short answers, but no FluidSim. But then if we talk about exam which will be done online, then it might be that we would use FluidSim, that I would give some task that you need to solve something and you need to calculate and use FluidSim and then give answers to Moodle.
Yes, it's clear. Thank you.
But topic for today is that we have some calculations called exercises here. It's a PDF which is visible for you, and there are different 5 different calculations that you should go through. And my idea is that I will once again give you some time so that you are able to solve them by yourself, or try to solve them by yourself as far as you can. And I'm here to help you, so if you have any questions you want to ask that, or you don't understand something, I will explain. And at the end, I will also show you the correct answers. but it would be very valuable for you so that you would first try to figure out the correct answers and the way to calculate them by yourself, because you will get this type of problems in exam, for example. So it would be very good for you if you would prepare yourself already. So basically, I will shortly introduce you the questions. The question number one, it's just that you need to understand what are the areas and things what are important or what matters in this case, where two different size cylinders want to be connected like this, so that the output oil of the minus chamber of first cylinder is let in to plus chamber of another cylinder, and the aim is that the speeds of the pistons would be equal or the same. So you need to just justify that how it should be dimensioned, but we are not looking any number, because any number is, I haven't give you any number, so it's just some let's say letters that matters, that what has to be the relation between certain things between the first and second cylinder. It is pretty simple at last. Then the question number two, there is this kind of a hydraulic crane, and it is told that down here is a hydraulic pump which is capable to produce this 68 liters per minute flow rate. And also the pressure is given here. It is 14 megapascals. And then we know that the diameter of the pipe here down is 19 millimeters. Then the oil travels within the pipe up here, and the distance between this and this place is 6 meters. And the pipe here is smaller. It's not anymore 19 millimeters, but it is 13 millimeters. And you should find out that what is the pressure. So pressure 2 up here. And now you can ignore all losses, so it's not a loss problem, but you should find out that how much pressure energy is converted to kinetic energy and potential energy, and then find out that how much pressure is left here. If you remember, I told you about this Bernoulli equation. Then number 3, this is a loss calculation. You should calculate all losses of the hydraulic system pressure line. And when I say pressure line, I mean a line between a pump and actuator, so that the flow goes one time through this directional valve. And then there are some other values told. So this is a loss thing. Then there is one just, let's say, question that find out what cavitation means in hydraulics. Maybe this is something what we can already now decide that you should not find out answers today, but this is something that you can search between the lectures, and then in the beginning of next week lecture we can talk about this cavitation. And final question number 5. it is very, very simple. I mean, the formula is very, very simple. You only need to calculate velocity. And we have been using this formula for velocity many times during this course already. So it's the flow rate divided by area. So Q divided by A. But you need to understand that what Q matters and what area matters in this case. There are different values given. It is told the pump is able to generate 3 liters per minute. Then you see 2 different flow control valves here, flow control valve A and flow control valve B. And it is told that the value of the set value of the flow control valve A is 3 liters per minute. It means that 3 liters per minute can pass this flow control valve no more. And the other flow control valve, it lets only 1 liter per minute oil through itself. So in this question, you need to at first figure out that what is the road for the oil. So it was told in the beginning that valve position is C+, and you see C+ here, and it means that this left side box will be active. And then you need to figure out where does the oil go, and also the returning oil, what is the road for it. And after doing that, you should figure out that which are the areas that matters and which are the flow rate that matters, and then put these values in this very simple formula. Speed is flow rate divided by area. Okay, so that was a quick introduction for the questions that I have. Do you have any questions at the moment about them or in general? It seems that pretty clear. So now I will give you time so that you can solve this, and after some moment I can show you the correct answers. And of course, if you need any help here, any assistance, you don't understand something, just ask. You can write me in the chat field, or you can just open your microphone and ask me.
So here we have an equation, the energy, Bernoulli energy equation, and there was still this delta P, but now I told you that we can ignore losses, so this delta P can be set to 0. And what is left is this one. And what we are interested in is this one. And it's pretty much then solving the equation. You know, almost everything already is given. The only thing what is missing is the speed. V1 and V2. And they are the velocities of the oil. So, this works in a way, this equation, that left side of it, you can imagine that all what you have here, it's this situation, and all that you have in other side of the equation is what you have over here. And it's about that energy will stay, but it will convert to a different form. So some part of the pressure is going to change to potential energy and kinetic energy. So we have here pressure energy, potential energy, and kinetic energy. And same terms in other side of the equation, but now just the amount of each is a little bit different compared to this situation. So we can see quite clearly that because we go 6 meters high, we have more potential energy here compared to this place. And when our diameter of the pipe is smaller, it means that the speed of the oil is higher here, which means that we have more kinetic energy. And because of those two things, we know that we have less pressure here. So we need to get an answer which is smaller than our original pressure, 14 megapascals. Unfortunately, Surai, the answer what you got, that is not completely correct. So when we start to solve this one, we get something like this. And if we say here that our distance 6 meters, we can decide that the starting point is 0 meter and the end point is 6 meters. So we can say that Z1 is 0 and Z2 is 6. We see then that if the Z1 is 0, this whole thing will be also 0. So it will be simplified a bit. It will be P1 minus rho multiplied by G multiplied by Z2. And then we can also take these factors rho as a constant here, so that we will get half times rho and then V1 power of 2 minus V2 power of 2, like this. I'm sorry, this has to be plus. And the thing what we don't know are the speeds. So speed of the oil, it's the flow rate divided by area of the pipe. And now it is this diameter that matters here in the case of speed 1. So 68 divided by 60,000, so that we will get cubic meters per second. And the area P times diameter power of 2 and divided by 4 like this. And we get 4. And in a similar way, V2 is Q divided by area 2. The flow rate is the same. Only thing what is changing is the diameter. And we get 8.5 meters per second. And now we are able to put these values to this formula. Power of 6 because it's megapascals. And then the final result is roughly 13.92 megapascals. So we don't get, of course, this kind of value, but we get 13.92 multiplied by 10 power of 6, but then I converted it directly to megapascals, so it's 139 bars. Do you agree? Is it clear now?
Yes.
And there was a question that what can you figure out about the result? Well, we can see that the pressure is not changing so much. It is less than a bar how much the pressure is converted to potential energy and kinetic energy. So what we learn here is that this kind of things don't matter so much in hydraulics. It's about losses what matters more. So in typical hydraulic circuit dimensioning problem, you don't need to calculate these things at all. But if you want to be very precise and you need to know precise pressures and how much is converted to a different form, this is the way how to do it. Okay. And actually, I suggest that we will continue so that let's first go through this question number 5. And after that, if we have time, we can go through also this losses question. But now put effort for solving this problem, and I will show you the correct answer for this one. And then if we still have time, then we will continue to do this question number 3. But the order where I'm going to show you the correct answers is that at first I will show you this one. Check valve. And we have this flow control valve. And what do you think if we have this kind of situation? Where does our oil go? Is it going through here or through here?
On the one-way valve.
From here.
Yeah.
Yes, that's true. So the road for the oil, if we have this C+ connection, it is starting from a pump and it is going through from P to A. And in here, always it chooses the road which is the easiest one for the oil. So here there might be some resistance, but this is an open road and the one-way valve is in such direction, in such position that the oil can easily go there. So actually this flow control valve A has no effect. Okay, then we have a cylinder somewhere. And the flow goes to the plus chamfer, and then at the same time, since the cylinder is moving, it's pushing out oil from the cylinder minus chamfer. And there is this other flow control valve, which is called B. And then there is this check valve. And they are connected like this. And at the same time, when the cylinder is moving, there is a flow coming out from the cylinder. And now this is blocked. It is not able to go through this check valve because that is in such position that the flow is blocked. So you might think that it goes until here, but no further, and it goes this way back to the tank. So we see that this is limiting the flow. Yeah. But before we calculate the final value here, we should check that what would be the maximum flow rate what this system can provide without any limiting. So maximum available speed for extending, and it is of course when we have the pump flow rate Q pump and then the area of the plus chamfer, so area plus. So if we want to find out what is the speed here, we need to use this flow rate. We don't have no limits in here, and the area of the plus chamfer. So the speed, let's call speed max, is flow rate of the pump divided by area of the plus chamfer, which is equal to area of the piston. So area of the plus chamfer was 4 square centimeters, and the flow rate of the pump is 3 liters per minute, so 3 divided by 60,000. And now it was not in diameter, but it was directly in an area that was told here, but it was in an not so nice units. So we need to convert these square centimeters to square meters. So it is 4 multiplied by 10 power of minus 4. Then we get square meters. And here an answer is 0.125 meters per second. So this is the speed what our system can maximum reach. But then if we take account this and check what would be the speed if this one is there and it is limiting. So effect of flow control valve B. Let's call it V limited. It is QB if we call the flow that can pass here flow B, divided by area of the minus chamfer, because it's this minus chamfer area which matters here. This is the amount of flow that is going through this flow control valve B. So it is 1 liter per minute divided by, now it is not the piston area, but it is the minus chamfer area. So the area minus is equal to area of the piston minus area of the rod. And it was 4 square centimeters minus 2 square centimeters. So it is 2 square centimeters. Like this, and we get 0.083, and we can see that this really is limiting because this number is smaller than the maximum speed. So with this kind of connection, this would be our answer, but it might be possible that this number would be smaller than this number, and then that would be the speed of our system if this is not limiting enough. Do you understand what I'm trying to say?
So could you repeat this? I mean, what's the reason that your velocity is the second one? If you can repeat.
Yes. So if we have a look at the circuit, what we have this certain flow rate that the pump is generating. That was this 3 liters per minute. And if we would not have this at all, but we would just have a connection like this, and from minus chamfer, the oil could freely go back to the tank, then our speed would be this one. But because the returning oil can't go freely back to the tank, but there is this flow control valve B, and that is such a device that it lets only certain amount of flow through itself, And this time it was told that it lets only this QB is 1 liter per minute. And that's the reason why we needed to check that how much the speed of the piston would be if we calculate it from the other side. So if we would calculate it from here, it would be this 0.125. But now when we calculate it, how much oil is coming out of the cylinder and how much is able to go here with this same formula, then we found out that it is a smaller number. And this is the one now who the unit which is limiting that how much is able to get through. I don't know, am I able to told it clear enough?
Yes, so the reason is that if you have a minor velocity, that is in this case, that's the minimum that you need.
Yes, yes.
Okay, yeah, it's clear now, thanks.
And still, I think it was told that please check the static situation. It just means that you should find out that how much force this connection or this cylinder areas and pressure is able to produce. It was 50 bars. And it is this piston area, of course, because our pressure is affecting here. We get 2000 newtons. And this 2000 newtons is bigger than load. So we can say that there is enough to move the load.
Sorry.
Yep.
I have actually created a fluid simulation, but it seems that I cannot move the cylinders, so I don't know why.
Okay, can you share the screen and I can check?
Yeah, okay. Here.
Okay, show me, do you have any load at the moment?
Yes. It's 500.
Okay, at this point, please make it empty.
Here?
Mm.
Oh.
Are you able to move it now? Oh, well, yeah, it should be available. You can have it, no problem.
Wait. I don't know why.
You need to press this valve. Keep it pressed.
Okay. It's okay. It's because it's a spring return.
Mm. Okay. Now you see it's giving this 0.083 exactly.
Yeah.
And now you can try what happens if you remove this other valve there. If you modify your circuit so that you will open that valve, for example, fully, so you don't need to take it away, but you can give there much higher, for example, 100, or no matter how big value you give there. Now the result will be this 0.125, as you see.
Yeah.
And I was telling that you should remove this 500 newtons, but that's not necessary. Of course, you can have it.
It's the same happen, right?
Yeah.
Okay. Yeah, okay. Thank you.
Okay, so now I think it's time to stop for today, and you could do the remaining tasks, try to do those tasks at home. There was this lost task, and then find out what cavitation means. Please solve them before next lecture, and immediately when our next lecture next week starts, I will go through the correct answers. So I'm not going to give you any more time to solve these problems in the beginning of the lecture, but this is a task that you should do at home. And then next week we are also going to talk about hydraulic fluids. Okay, that's it. So see you next week.
See
Bye.
you.
Thank you. Goodbye.
Bye.
Thank you.